Welcome to this video where we're going to talk about one way which you probably have used already for calculating a system where we're pumping a liquid. And then in part two, kind of the follow-on section of this video, we're going to talk about a different way that we can think about the exact same problem. So in this video, we're going to go through kind of our standard methodology. We'll see that we run into some potential issues with that. And then we'll also see in the next video this alternative solution. So in this video, you can see the problem statement here. We have an ideal meaning adiabatic and reversible. An ideal pump which pumps saturated liquid. So that's why we have saturated liquid here, 60 degrees C, zero quality, meaning saturated liquid, and it pumps it to a final pressure of 3 megapascals. It's going to remain liquid. So we're going to be, the outlet will be a compressed liquid. There's going to have to be a work input, which I have labeled here as WP, into the system in order to accomplish this. We can go through and do our mass balance. Our mass balance is super easy. What comes in must come out. Our energy balance is a little bit more complicated other than the fact that this is an ideal pump, so we solve these kind of the same. So if it's an ideal pump, that means kinetic energy equals 0, potential energy equals 0, and it's adiabatic, so heat transfer equals 0. So our simplified energy balance, is just delta H dot equals minus W. And this should be an energy balance that we become fairly familiar with seeing. We're going to use the same energy balance for pumping, for a compressor, and for a turbine. Okay, so to look up any values, whether we're looking them up in tables or in Cat3, we need two pieces of independent information. We have two pieces of independent information for the inlet, what we'll call called here state 1. We only have a single one for state 2. We'll get there in a second. So our 2 for state 1, we have a temperature of 60 degrees and a quality of 0. That means we're going to look, starting in table B.1.1, which is saturated. We're going to find 60 degrees, and then we can find everything that we want. So here would be the pressure, the enthalpy, and the entropy. So we can find all of those, right? X equals 0 means we're looking right at this column, the saturated liquid column, HF or SF. If we wanted to find the specific volume, we'd look at VF. Specific internal energy, we'd look at UF. But those are all the values that we would want for that. Okay. For state 2, we have one piece of information, which is the pressure. Our second piece of information is something about the process. It's an ideal pump, adiabatic and reversible, so that means that delta S equals 0. So this is our second piece of information. We actually know the entropy, 8.311 kilojoules per kilogram Kelvin. That second piece of information is from the process because we know that this is an ideal pump. Okay. So now we're going to be looking, instead of the saturated tables, we increased the pressure, we compressed the system. So now we're going to be looking in the tables for compressed liquid water. And we're looking for these two values, this pressure, 3 megapascals, and this entropy, 0.8311 kilojoules per kilogram Kelvin. So we find pretty quickly, we have our pressure is in between two values, right? So we have 500 kilopascal, 2000 kilopascal, and 5000. So we're in between these two sections of our table, 2000 and 5000. And our entropy is going to be, right, it's 8.311. So it's actually, if we look at the entropy column, it's in between those two values, and it's in between those two values. So our temperature is going to be somewhere between 60 and 80 degrees, and our pressure is between those two values. So we have we'll actually do it here in a second, a double interpolation. So let's go through and think about how we would actually find that. Okay, so we're looking for 3 megapascals and an entropy of 0.8311. So this is, I'm just pulling kind of this section of the table, right? Those are the numbers that we're interested in, and the temperature, and then again the temperature values and those values. I'm just pulling these all out and making a table like this for them. So you can see we have 60 degrees, the enthalpy is 252.77, the entropy is 0.8300. That would be the data from up here, and I'm doing the same for all of those points. Now, what we really want is 3,000 kilopascal, and this entropy we want to find, well, maybe temperature, but we really want to find enthalpy H. So we have to do some serious interpolation. So first we have to take and figure out the enthalpy at 3,000 kilopascal and 60 degrees Celsius, and the entropy at 3,000 kilopascal and 60 degrees Celsius. So we're, okay, first interpolating between this value and this value at 60. If we do that, we get 0.8295. I'm not going to actually do all the plugging in, but you can see we're in between those two values, a little bit closer to 0.8300 because, right, we're a third of the way between 2,000 and 5,000. And same thing for the enthalpy. If we interpolate between those two values, 252.77 and 255.28, we get 253.61. We can do the same thing now at 80 degrees Celsius. If we do that, let's do the enthalpy first. We're going to be between 336.44 and 338.83. It would be exactly 337.24. And similarly, for the entropy, we would be 1.0732. Okay, the actual values that we want now are these values, right? We know, okay, so we've kind of gone, now we want to find, right, basically use those two values to kind of figure out, you know, what percent of the way. You can see I'm closer to 0.8295 than 1.07. So our values should be closer to 253.61 than 337.24. And we can do now a second interpolation to get to these two values. If we go through and actually do that, we get a temperature of 60.13 Celsius and an enthalpy of 254.17. Kilojoules per kilogram would be the units on that. So you can see, even without me actually plugging in the numbers while I'm talking about this, I did that beforehand, we have to do quite a few interpolations. We actually have to do, if we count them, 1, 2, 3, 4, 5, 6 different interpolations in order to get our two values. 60.13 for our temperature and 254.17 for our enthalpy. Quite a bit of legwork, certainly a lot of area for some mistakes. If you really want to check your interpolation skills, pause the video, you know, hide all this and see if you can find the same values that I did for temperature and enthalpy. Okay, so you may say, this is why we have Cat3. So let's see what values Cat3 gives us. Hopefully it gives us basically the same thing. So we'll pull up Cat3. Okay, so we're looking at the tables for water, right? We're looking at temperature or pressure and entropy. You can see I've already plugged this in before. Pressure and entropy, and what values do we get? A temperature of 60.13 and an enthalpy of 254.1. So for Cat3 we got 60, use blue, 60.13 Celsius and 254.1 kilojoules per kilogram. So Cat3, certainly easier than doing all our fancy interpolation, gives us essentially the same values, right? We got, well, we got a little bit different value for the enthalpy. We got basically the same value, at least to 4 significant figures for the temperature. Okay, how we would normally solve this is, right, once we have the enthalpy in and the enthalpy out, then we can do an energy balance, right? Our energy balance, our simplified energy balance was this. That's what we did at the very beginning. We can break that apart into a mass flow rate and a specific enthalpy difference and a specific work. That simplifies to just this equation here. Minus WP equals H2 minus H1, where our H2 is, say it'd be 254 we'll use our interpolated value. Well, let's use our Cat3 value, 1 kilojoules per kilogram, minus our H1, which if you forget what that was, we looked that up a little ways earlier. We looked that up, that was this value here, 251.11. So minus 251.11 kilojoules per kilogram. So we get that minus WP equals 3.01 kilojoules per kilogram. Which, right, means that WP equals negative 3.01 kilojoules per kilogram, where our negative sign means our work is going into our fluid, right? We're pumping this fluid, we're putting work into the system. That's why we get a negative sign there. And we're putting in about 3 kilojoules for every kilogram of water that's going through our pump. So this is the answer that we get when we do kind of our standard problem-solving technique. It works fine as long as we're using Cat3. It's certainly pretty cumbersome if we're using tables. So we're going to look in the next video at a little bit more elegant way to do basically the same thing.